defined sequences. We already talked about it very mildly, that if you're given a sequence such that the general term of a sequence is defined in terms of some of other its terms, prior terms, then that sequence is going to be called recursively defined. So let's recall that definition again. Okay, recall that. A sequence AN is said to be recursively defined. That's the expression that we're going to use for the next 4 sections. Okay, recursively defined if AN, the general term, is defined in terms of some other terms. Depends. Okay, this would depends upon some of its previous or prior points, prior terms. The prior terms are going to be AN minus 1, AN minus 2. It can goes on forever up to the A1. Okay, like the one that you got on the quiz. You know, that was not official. But now we are going to make it official, okay? So for example, the first one, if a sequence would be given to you, okay, suppose AN is equal to the 3 times AN minus 1. Of course, this N starts from 2. Then they have to give you the A1. So A1 is equal to 2. Then if you want to find the A2, you know that. You go back and you substitute N equal to 2, you get the A2, and then you continue. So this is going to be recursively defined sequence. And AN is going to be a recursively defined sequence. Something that you do over and over and over, and there is a relationship that keep you going. So that the relationship is going to be recursively defined. Any question? Now, some famous one that you must know them by name. This is one of them, Fibonacci sequence. Okay, this is the one that you use in your field quite a lot. You must know everything about this sequence. Okay, what's going to be Fibonacci sequence? Okay, this sequence is defined by Fibonacci is an Italian mathematician. Okay, we introduce this sequence first. So a Fibonacci sequence, okay, be denoted by Fn for the Fibonacci. Okay, it's defined by each term is the sum of its 2 previous one. Fn is Fn minus 1 plus Fn minus 2. So those indexes cannot be negative, so you have to start the n by 3. Okay, n greater than or equal to 3. So you have to give us a F1. F1 is equal to 1, and F2 is equal to 1. In some books, they start with, they start with the F0 and F1, and then they give you this relationship in terms of the, n greater than or equal to 2. But I just followed the notation of your book because you have a couple of problems that you have to solve. Okay, so this sequence is going to be called Fibonacci sequence. Why it is popular? You must know the terms of this sequence, and you can use it anytime you like in this course. So let's try a couple of terms. So if you want to find the F3, we go here and replace n by 3. So the previous term would be F2. And one more done, that give F1. Add the F1 and the F2, both of them are 1. So that give you 2. So the third term of a Fibonacci sequence is going to be equal to 2. Okay, question? Let's have another one. F4. F4 is going to be 1 down, so that give F3. And one more down, that give F2. F3 is equal to 2 and F1 is equal to 1. So the result would be 3. So F4 is equal to 3. Again, we can go on to get all the other terms. So the terms of the sequence, we start with a 1, 1. Then you add these 2, that give you 2. Then you add these previous 2, that give you 3. Okay, and 2 and 3 would be 5. 5 and 3 would be 8. 8 and 3 would be 13. Okay, 21, etc. This result is going to be called the Fibonacci numbers. Okay, these are called Fibonacci. Okay, Fibonacci numbers. Okay, so that's going to be this famous sequence. There are quite a lot about the Fibonacci numbers or the Fibonacci sequences. There are some stories, related to this one. Most of them are false, but there are some nice ones mathematically. This type of sequence is going to be using coding theorem, okay, or theory. You will see it over there, okay. And there are many other properties. One famous property is that if you consider the ratio of any of these, okay, so if you consider the ratio of any two Fibonacci number, fn plus 1 over fn, you see, if you start with, 3 half would be 1.5. But if you start with a 5/3, 8/5, 13/8, these are going to be something like 1.69. Okay, almost. But it's going to be, in the radical form, and this is called golden ratio. Okay, golden ratio, and there are some other, story related to this one. In distance form, if you like, but if you want to read it, you can read it for yourself. We look into it as a sequence. When we used to have a face-to-face class, and we asked somebody to come and tell us something Fibonacci numbers, there are quite a lot on YouTube, and that some property of the Fibonacci numbers. Okay, so but we stay with this sequence. And these are going to be 1, 2, 3, this sequence Fibonacci numbers. And later on, we are going to give you the exact format of the Fibonacci sequence. So knowing it is part of the deal. If you write a couple of terms of a sequence and you find out that the numbers are going to be in this order, so you can claim that this is Fibonacci sequence and be accepted. Okay, any question? There are different stories. One of them is that the oldest one. If you take a one pair of rabbits with different genders and leave them alone in an island, the rabbits, they are not going to give birth to a new one until they are 2 months old. So this is going to be the starting point. After the first month, you still got one pair. When we get to 2 months, you did have one pair. They reproduce another pair, so you get 2 pairs. Then we get to the 3 months, We already got the 2 pairs, but there is one that's going to be two months old. So that give it 3, and you can keep going. So they got it Rabbit Islands. And of course, there are more serious examples that you will see one of them when we get to your next, next practice quiz, if you like. Okay, any question? But knowing it is part of the deal. Just a Fibonacci sequence. If you say Fibonacci sequence, you must know that this relation and the starting point. Okay, you may have to use it for some purposes. That's one of them. Any question? So it's a very popular and famous recursively defined sequence. There's another one. This next one, the format is interesting. Okay, this is example, next one. This example is famous. They call it Tower of Hanoi. Hanoi. You know that Hanoi is the capital of Vietnam. I'm going to tell you what's going to be the story behind that. I mean, just whether it's true or not. Now, this start with a game, and eventually would give us a very nice sequence that you have to know the idea. Now, what's going to be the game? The game is that suppose you have a table, for example, here, and these are going to be some big or iron bar, if you like. You have this 3 here. Okay, so call it number 1, number 2, and the number 3. So what we'd like to do, we have a number of the disk here. I'm going to start with a 3. Okay. So in this case, I have 1, 2, 3 disks. And so what I would like to do is I would like to get them, move them from number 1, if you like, to the number 2. I want to know how many moves or movements do I need, okay, to transform or transfer these from the 1 to the second one. But there are 2 conditions. The first condition is that at any time, you can only move 1 disk. And the order of the disks must be from the big one right at the bottom, okay? So as you go on, the disk should get smaller and smaller, okay? So for example, we have 3 here. So what we'd like to do is we'd like to move these 3 from 1 to 2. And we know that how many moves do we need with the condition that I talk about it. At any move, you can only just take one of them. And anytime you look at it, the bigger one must be down the bottom. Anyone want to try? So let Hn, this is expression that you have to know. Hn is what? Hn is the number of, let's say, needed moves, okay, to move or to transfer or transform n disks and disk. Okay, in this case, n is equal to 3. And this from number 1 to number 2. Okay, anyone want to try to see what will happen for if you have a 3 disks?
Move the small disk to 2.
Okay, let's see. So this is it. So that would be 1 movement. Okay, then
Move the middle size disk from 1 to 3.
that's it. So this is going to be the middle one. Yes.
Now move the small disk from 2 to 3.
I'm sorry, that's going to be, that's it.
Now the large disk from 1 to 2.
Yeah, the point over here is, yeah, you're right. The point over here is that you see the idea is you have to release this one if you like. So yeah, let me just do that one, then I tell you. Yeah, that's it. Then,
And the small disk from 3 to 1.
yeah, you see that when we get to this part over here, you see we did 1, 2, 3. Okay, 1, 2, 3, 4, if you like. And then what is going to be the case that we're going to have? You see, we did 1, 2, 3, 1, 2, 3 moves in order to release this last one. So you get 1, 2, 3 over here. Then you have one extra action to put the bigger one into the second one. Now you are going to do the same procedure for this one, because what you did, you're just moving 2 disks from 1 to 3. So the number of the moves that you need to continue is going to be the same as the one that you did. Okay, 1, 2, 3. 1, 2, 3 over here was exactly the number of the moves that we need in order to move, okay, 2 of these, if you like. So by 3 moves, we should get to the next part. Okay. So what was that? This is the one. Yes. I'm sorry. That is going to be the case first. Okay. What next?
Then you move the middle size disk from 3 to 2.
The middle one. And of course, the last one is going to be
1 to 2.
1 to 2. Very good. So it should be 7. Yes. 1, 2, 3, 4, 5, 6, 7. You see, that gives us an idea for the one that we are going to do in future. So what we did really is, you see, this is what we did. We want to find the number of for the H3, the number that we moved. So what we did over here is we just move 2 of the disks from 1 to 3. So the number of the movement was H2. Okay. Then we did one extra action to move the isolated one to the 2, and then we'll repeat the same procedure to get back. You see, so this means what you did really is going to be twice of the H2 plus 1. And the operation that you did resulted in 7. You see, because you have to think about it mathematically, inductively, if you like, to get the final answer. So if you do the same procedure, if you want to move the n disks, so what you are going to do is you have to remember release the last one. So you need hn minus 1 move, okay, to put all the top as we did it from 1 to 3. Then we do one extra, okay, we do one extra move. You move the isolated one. Then you do the same thing to go back. You see, you are going to get the hn equal to the 2hn minus 1 plus 1. And of course, n here is going to be then equal to 2, and you have to give us the h1. h1 is equal to 1. So look at this one. That gives you a nice recursively defined sequence, if you like, for the, we call it for this, okay, for the tower. Okay, any question? So what we did, you see, this is it, smaller. This is what we did. This is the starting point. So what do you have? So what we did, we can, this is going to be n disks, okay? This is going to be the n disk. So we we are going to, okay, we transfer a n-1 of the disk here, then there is going to be a leftover when you transfer it to the other side. When you transfer it to the other side, there is going to be, let me write it down here, sorry. You see, to give you the idea of the induction. See, this is what will happen. This is the, okay, the starting point, if you like. This is going to be the starting point. So what we did, we are going to transform hn, n-1 of these. You see, this is the n disks, and this is going to be 0, 0, if you like. Over here, we get the 1, and we get the n-1 here. And there is nothing here. Okay, so that's just one action. One action. So the number of the action that you need, it was hn-1. Because if you believe that hn can be done for n disk, so with hn-1, you move it to this side. Then the next step was, with one move, you see, with one move. So with one move, you are going to move this last one over here, you see, to this part. And the middle one is still that hn-n-1. Okay, so when you move them to the other side, the result is going to be okay. You see, the result going to be this one. And this is n-1. And then you do the same procedure with hn-1. So you get it here, which is going to be, okay, which is going to be n. So basically, the number of the move that you need is, you move hn-1 from one part to the other part. Then there is going to be leftover 1. You move that leftover. Then you do the same procedure to get back. So that's what hn would be, 2hn-1, okay, plus 1. Or n greater than or equal to 2, and when h1 is equal to 1. It's a very nice one. This is called the Hanoi's Tower. Okay, this is called, okay, that's it, Hanoi's Tower, the relation, if you like. And later on, we are going to prove that by induction in a minute. We are going to show that hn would be 2 to the n-1 for n equal to the 1, 2, 3, etc. You see, this is very, very popular one. I'm going to prove it for you in a minute. Any question? So these are the type of method or thinking that we're going to do. Just our operation we call inductive operation that we're going to do. As we did it for the procedure of the induction. Okay. So what I'm going to do, I'm going to show you how I'm going to solve this type of equations. These equations, when they are easy, when you go with the hn to the h-1, we can solve it easily. And the procedure is going to be, I'm going to show you. We are going to guess what is going to be the solution, and you have to prove your guess by induction. If it's go to the n-2, it's not easy to use induction to solve it. We are going to show you a kind of algebraic method to do it. But you have to be able to take care of that induction part first. Any question? Okay, let's see how we're going to do it. Now, the story about it is quite interesting. You see, this would be 2 to the n-1. And some people believe that, there is a kind of, a church or something in that Hanoi, or there are some people that they are moving golden disk, and the number of the golden disks are 64. You see n is equal to the 64. And they are going to do this game by this 64. And they believe that when they are done, that would be the end of the world. But if you use your calculator and put 2 to the 64 minus 1, would be quite a lot. So we are going to be safe. So, this is kind of some people like stories. So your serious job is this one, this method, because we give you similar problem and you should be able to solve it for us. Okay, so the problem is going to be if hn is equal to 2hn minus 1 plus 1, okay, and h1 is equal to 1, would like to solve it. Find the formula. A formula for hn. Okay, let's say I'm going to find the formula. There are two different methods to do it. One is just list some of the terms. List some of the terms and check to see if they are following a special pattern. Okay, these are going to be easy cases, so you'll be able to find it. Those special pattern. So let's try. List some terms. Note that. Start with the h1. H1 is 1. Done. Okay. Get more. H2. Remember this is your formula. H2 will do what? 2h1 plus 1. H1 is 1 plus 2, so that gives it 3. Okay, try another one. H3 is 2h2 plus 1. But H2 is 3. 2 times 3 plus 1. 6, 7. Write another one. It's going to be 2h3 plus 1. H3 is 7. That gives you 15. Then you think about it to see if you can write it down. These forms that you have are going to be easy. It's going to be something like, a number raised to n, something similar. So you have to check, for example, to see if they are powers of 2, powers of 3, powers of 5. Okay, this is the way we think about it. So for example, for this one, it's the way you think about it. Say, oh, and this is 3. If it was 4, would be 2 squared minus 1. This is 7. If it was 8, would be 2 cubed minus 1. This is 15. If it's a 16, it's going to do 4 minus 1. So that gives you an idea of what's going on. So we are going to rewrite that h1 is 1 is equal to 2 to the something, 2 to the what? So this is going to be, okay. So to the first power minus 1, that give you 1. Then h2 is 3. So 3 would be 2 squared minus 1 because the 4 minus 1. h3 is 7. 7 is 2 cubed minus 1. Now we get the idea. Even h4, 15 would be 2 to the 4 minus 1. Okay, so now you can claim that hn must be 2 to the n minus 1. Okay, any question? But that's a claim. So, okay, so this is going to be a claim. Okay, so what we are going to do is we are going to prove this claim for you. So what is going to be the claim? So you claim that hn must be 2 to the n minus 1. okay, for all n greater than or equal to the 1. This is going to be your claim. Okay? Any question? But you have to prove your claim. And you know that. How we're going to prove the claim? We prove the claim by using induction. This is where the procedure of the induction is coming. Okay, any question? Remember, you're not done. Some people, they leave it. They say, oh, I can see it. Yes, we can see it. But you didn't prove it. Okay, so you claim and then you prove it by induction. Now, how are we going to prove by induction? Proof of the claim. Okay, proof of the claim. Remember, the induction, you need the Pn. So what's going to be a Pn? Suppose, okay, you suppose that the Pn, remember Pn is this statement, that the Hn is equal to the 2 to the n minus 1. Sorry, 2 to the n minus 1. So that's going to be Pn, but I should prove, or one should prove, that Pn is true. Pn is true for all n greater than or equal to 1. Okay, so it's a nice induction procedure that you have to follow in order to get your result. Any question? So we are going to go over it to prove it. I'm going to go to the next page. Are you done? No. You know that this is going to be easy procedure. So the basic step is that you have to prove it's true for n equal to 1. So if n is equal to 1, your formula give you h1 equal to the 2 to the first minus 1, which is going to be 2 minus 1, which is 1. h1 equal to 1, yes, it's correct. Because if you want to move one disk, you just need one action. Okay, so B1 is true. B1 is going to be true. Any question? Inductive part. It's ordinary induction. Okay, it's ordinary induction. You fix it for K and you will get it. So suppose K greater than or equal to 1 is given. Such that B1 is true. Sorry, such that BK is true. Remember, you fix it for K and you prove it for K plus 1. So what does it mean? So PK means HK is equal to the 2K minus 1. But you want HK plus 1, how are we going to get it? Say, oh, note that. Remember, it's a recursively defined sequence. HK plus 1 is equal to 2HK plus 1. So it's going to be 2 times HK. What's the HK? 2 to the K minus 1 plus 1. Distributed, that's going to be 2 to the K plus 1 minus 2 plus 1. So that gives you 2 to the K plus 1 minus 1. And that's exactly what you want to prove. Okay, because you want to prove PK plus 1. So PK plus 1 is true. PK plus 1 is true. And by induction, we are done. By induction, Pn is true. Pn is going to be true. Okay, so this is how we prove this type of equations, if you like. Of course, these are very mild one. If you make it complicated, we can't do it. Okay, but we can do this type of operations that we're going to have. Okay, any question? So this is one type of idea. And the one that we have is most of them are kind of geometric sequence, but remember nothing, you're not going to use anything from calculus or from algebra. We use only, we guess and we prove of guess, okay? In your book, they give you the formula for the geometric sequence, okay? But we wanted to use, apply the induction only. In some of the problems of the book, they ask you to use the formula. Yes, you can do it. But on the test, we are not going to give you anything of this type, okay? So be careful. So I'm going to give another one. Okay. In your book, they talk about, they just describe it on 5.6. And in 5.7, they talk about solving. So we are going to be in 5.7. Okay. So let's go to the next page. Any question? So in 5.6, they just introduce this famous one, Fibonacci one, okay, and the Hanoi towers. But in 5.7, they are officially talk about solving this type of equations. Very mild one. Okay, so solving, there are going to be two groups. One group can be done algebraically, if you like, and the other one is going to be induction. Okay, they call it solving recurrence. Okay, that's it. It must be 2R. Okay, recurrence. What is going to be recurrence relations? Just those recursively defined equation that in your book they call it a recurrence equation. Okay. So what we are going to do is, let me just give you this expression first. If a sequence AN is defined recursively, okay, is defined recursively by an equation, then this equation is going to be called recurrence relation. Then the equation or that equation is called a recurrence, okay, a recurrence relation for the given sequence. Okay, if they say solve the following recurrence relation, you know what they are talking about. We're going to classify them nicely in the next, in the next section, but for the time being, we're just working on this, the one that we can do it by induction, okay? Example. So we want to use induction. We give it the instruction, okay, instruction on the test, but these are the only method that, this is the only method that you have. Use induction to solve. Okay, to solve the given recurrence relation. They are very limited, the one that you have. It's a kind of geometric one. because we want to make sure that you know the method. Otherwise, the complicated one is going to be used, solved later on. This is a geometric one. AN equal to 5 times AN minus 1 for all N greater than equal to 2, and the A1 is equal to 2. So you want to find this one. Call it geometric because each term is 5 times the other one. It's a kind of geometric sequence with a common ratio of 5, if you are familiar with this type of expression from algebra, but forget it. You have to do it using mathematical induction. Now, how are we going to do it? Again, list some members to see if you can guess what is the form of the general solution, and then use induction to prove it. Okay, there you are. Solution. Start writing some of them. A1 is already given to us 2. Okay, find the A2. A2 is 5 times the A1. So it's going to be 5 times 2, which is 10. Okay, go over A3. A3 is 5 times the A2. And A2 is 10. So that gives a 50. A4, 5 times the A3. 5 times 50, 250. Okay, now we are going to rewrite it, check to see if you can write it down as a power of a number. Okay, so the power is going to be, okay, so the power is going to be in terms of the 5. Look at the 10, 2 times 5, 50, 2 times 25, 2 times 5 is square. Okay, and this is going to be 5 times, okay, we get this one over here. Okay, for the 250 is going to be what? Is going to be 2 times 125. 125 is 5 cubed. So this is the way we are going to arrange it. We decided that the powers of the 5. So A1 is equal to 2. We write on the 2 times 5 to the 0. Okay, that's the first one. Now we continue with the others. A2. A2 was equal to the 10, so it's going to be 2 times 5 to the first power. A3 was 50. It's going to be 2 times 25, 225. So it's going to be 2 times 5 squared. Okay, then the A4 is 250. Is going to be 2 times 125. So it's going to be 2 times 5 to the third. Okay. So what is AN? Who wants to try? AN. You see the A1 is 5, 2 times 5 to the 0. 2 times 5 to the first. 2 times 5 to the second. And 2 times 5 to the third. Anybody want to try AN? Look at the pattern that we have. 2 times 5 to the third, that was 4. 2 times 5 to the second, that was 3. 2 times 5 to the first, that was 2. So what's an?
2 times
2
5 to the n minus 1.
That's it. 2 times 5 to the n minus 1. You see? You should see the, the pattern that you're going to have. So this is going to be true. You claim that for all n greater than equal to 1. Any question? So this is, as I told you, if it's going to be complicated one, it's not possible. But it's not going to be a difficult one. So you write a couple of them. I'm going to show you another method, but this method is not bad. And when you do a couple of them, because they are going to be repeated, so you know the idea. Okay, so we write a couple of them to get the addition done, but you're not done. You're not done. Remember, some people leave it. No, you haven't done it yet. So that's only the claim. So you have to prove this claim. Okay, so your claim so far is consistent. Any question? So we just write a couple of them to get it. We know there's going to be powers of 5. So we just compare the index 4, 3, 3, 2, 2, 1, n minus 1. Okay, but this is just a claim. You're not done. So now you can, I claim that the an is 2 times 5 to the n minus 1. Okay, and I claim that it's going to be true for all n, okay, then equal to 1. Okay, now prove the claim. How going to prove the claim? Of course, induction, basic part. Any question? Now the basic is n equal to 1. If n is equal to 1, a1 would be 2 times what? 2 times 5 to the n minus 1 would be 0. 5 to the 0 is 1. So I give it 2. So a1 is equal to 2, which is true. Because a1 is already given to you, remember? a1 was one of the conditions. So p1 is true. Okay, therefore p1 is true. Any question? Now, inductive part. So what you do? You assume that it's true for k and you go for the k plus 1. So suppose k equal to 1 is given such that pk is true. pk is true. What does it mean pk is true? Therefore, pk is true means your formula is true for k. ak is equal to 2 times 5 to the k minus 1. But you have to bring the k plus 1. Say, oh, note that. What is ak plus 1? Remember the recurrence relation that you have. What you have? Each term is 5 times the previous one. So ak plus 1 is 5 times the previous term, which is 5 times ak. Substitute, like the one in your quiz. 5 times ak. Times it by what? Put a bracket here. 2 times 5 to the k minus 1. Flip the 2 and the 5. 2 times 5 times 5 to the k minus 1. Now 5 times to the 5k minus 1 would be 5 to the k. That is exactly what you want to prove. Remember, this power is always 1 done, but 5k was k minus 1. So pk plus 1 is true. And by induction, Pn is true. Pn is true for all n greater than equal to 1. And you're done. Okay, so your claim is true. The claim that the an is equal to the what? 2 times 5 to the n minus 1 for all n greater than equal to 1. See again, the procedure is a kind of, we call it inductive procedure. Okay, to get these numbers done. Any question? So in this method, we just try, see, we write a couple of terms and then, we guess what's going to be the final answer. And then you have to prove your claim. Any question? This method is nice one. There's another one in your book. The way I did it, we call it move forward. I just start with the, okay, start with the A1, A2, A3, and get these numbers. Oh, okay. Okay, so there is going to be another method that we can do to check this one. In your book, in some of the problem, they ask for this method, but you have a choice. You can use either method you like. So let me explain that one too, then we are done with this section. Method 2. But you have the option, you can use either method. We don't mind. They call it iteration method. Okay, iteration. Iteration method is that, so we go with suppose you want to solve this one. Okay, solve an equal to the 5, an minus 1, when n is greater than equal to 2, of course, and the a1 is given to you. Look at this method. Is it the method that I gave you? It was moving forward. I start with the an, then I find the a2, a3, a4, etc. This method is moving backward. What does it mean backward? You see, look at this one. Some people like it. This is an equal to the 5 times an minus 2. The same method, what we do is, if an is 5 times a minus 1, what is an minus 1? You see, you repeat this formula, but for an minus 1. So this is going to be 5 times, you repeat the formula for an minus 1. So it would be 5 times 1 done. 5 times what? An minus 2. You see, this is the formula an, 5an minus 1. So we start with the an minus 1. It's going to be 5 times the previous term, which is an minus 2. So we get 5 squared times an minus 2. Now repeat the formula again for an minus 2. So what's going to be the result? It's going to be 5 squared. Again, it's going to be 5 times. 5 times what? An minus 3. So that will be 5 to the third. An minus 3. You see? Sorry, an minus 4. So so far you get an equal to the 5 to the third. Okay, an minus 4. And we can keep going. If you keep going, you are going to add the power to the power of the 5, and you reduce this index, you see? You start with n minus 1, n minus 2, n minus 3, that. So we get to the situation that this is going to be 5 to the, you see, I'm going to go with the an, subtract, I want to get to the a1. So I subtracted from n minus 1. You see, 4, 3. I got the, okay, this is it. So when we get the, start with n minus 1, 5, n minus 3, that give you 5. So what I do is I just keep going to get to the, okay, to get to this part. So what is going to be this result? So the top over here is going to be n minus 1. Okay. So the result is, but if you have n minus 1, it gives you n minus n plus 1, which is 1. So that take you to the 5 to the, okay, that take you to the 5 to the n minus 1, which is going to be times the a1. Okay, but the a1 was equal to what? a1 is equal to 2. So that gives you the fact that the an is going to be 5n minus 1 times 2. So the an would be 2 times 5 to the n minus 1, or all n greater than equal to 1. See? But again, this is going to be a claim. Then you have to prove this claim, okay? So you have to prove the claim by induction. You see, this is two different methods in order to find your general term. Moving forward or going backward, if you like. But I like the previous one, the forward one, but it doesn't matter. If it's going to be on the test, it's going to be one on the test. In your book, there are two sets of assignments. One of them asks you to, when you go back forward and backward, sometimes there is only one in your book. Technically, it's a tricky one. I may talk about it for you next time when I get the number from your book, because I've seen some of the people, they ask as a question to get these numbers. Yes, question, Edgar?
Can you explain the part where it goes from 5 squared times 5 an minus 3, and then it's equal to 5 to the third?
You see, we start with at the beginning. You see, each term you reduce this index by 1 unit, okay? So this is 5. That takes us at 5n minus 2. So it's going to be 5 squared n minus 2, okay? So as you can see, 2, 2. You get the same one. Then n minus 2 is going to be 5 what? 5a 1 dot. This is n minus 2. When you go down, that gives n minus 3. So that gives 5 to the third, a n minus 4. Okay?
So
if you want to go one more, you say, let's go one more.
right there, why does it change from an minus 3 to an minus 4?
Oh, I know what you mean. Sorry, you are right. You are right. Yes, that's in fact the one that I need. Yes, that was a 5q an minus 3. Yes, an minus 3 is the one. Okay, we can go one more. It's going to be 5 to the third, 5a, and now n minus 4. Okay, so that will give us what? 5 to the fourth, an minus 4. Okay, so the idea is going to be exactly the same thing. You see, 4, 4, 4, 4, 3, 3. So what I did, I went down to the n minus 1. So n minus 1, this must be n minus 1. 5 to the n minus 1. Okay, 5 to the n minus 1, an minus n minus n. I simplified that, give a1, and then the rest would follow. Yeah, that was n minus 3, not n minus 4. Okay, any question? You can do it with the Hanoi Tower, but that would be more complicated because that would give you a geometric sum. I may try one more for you next time. Okay, so this is going to be section 5.7. I'll leave it here. Continue next time. And there is one more section 5.8 that would algebra. We call it algebraic method. Nothing to do to the induction. If you have done a differential equation course in calculus, it's the same method that we use, all over there. If you have done it, you have something we call it linear differential equation of the second order. And that method would be, we copy that method here, and that give a very nice version. Okay, I'll talk about it on Wednesday because I don't have time here. Okay, any question? So read these examples. As I told you, this is just the induction method. It can be applied only to the, we call it recursive relation of the first order, n-1. If it's going to be plus something like 3 times an-2, is very complicated. We don't do it. We use algebraic method. Okay, that's it for today. I have to go. Any question? So 2 more sections from this chapter. 2 very interesting ones. We try it. We try one of them on Wednesday, and then we finish it by next week. And when we finish this chapter, the rest are going to be just, we get something from some topics in each chapter. It's not going to be consistent like the one we did so far. Yes, question?
When you have time, can you update all the homework that will be collected next Wednesday?
Next Wednesday? Is the quiz next Wednesday?
Yes.
I checked that, yeah.
Okay, thank you.
Yeah, it's going to be everything up to the end of this chapter. If you
Okay.
want to get something, because we have 2 more sections. We finish that, we give it, yeah, I do that. At the end of this, I check the previous one and I update it for you, yes.
Thank you.
Okay.